Okay, so this video is the third in our series on probability, where we're starting at looking at discrete probability. Now, normally in a normal year in the VCE Maths Methods course, we would probably spend the next 3 lessons looking at introducing the idea of a discrete random variable and looking at how to work with distributions of discrete random variables and features of those distributions. Now, technically, discrete random variables are not in the course for 2020. With the reduction in content due to COVID this year, discrete random variables are out. So whilst I'm not going to set you the work in this section to do, I still think it's important that we talk through some of the ideas around discrete random variables. So I've combined some of the ideas together here because I think it still provides important background before we begin to speak about the binomial distribution, which is a specific example of a discrete random variable. So I think it's important to go through some of the ideas, particularly getting an understanding of what the sort of different measures of centre and spread mean and represent before we look at those specifically in the context of the binomial distribution. And I'll do the same with the continuous random variables, give an overview of continuous random variables before we look specifically at the example of the normal distribution. Okay, so let's get into it. So basically a random variable assigns a number to each outcome in the sample space. So when we've looked at probability before now, sometimes our sample space could be things like head or tail. Or, you know, if you're tossing the coin 3 times, it could be head, 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 tail, tail, head, tail, head, whatever it might be. Okay, so what we want to do though is make sure that when we're dealing with a random variable that we always assign a numerical value to each outcome. And a discrete random variable means that the random variable can only take distinct, usually integer values. Okay, so often we would, the distinction between a discrete variable and a continuous variable is that discrete is usually a countable quantity, the number of people with red hair, the number of times I observe a head, the number of 6s I see when I roll the dice, the number of red cars that drive down the street today, whatever it might be. Those are usually, so countable quantities would usually be measured as discrete variables, whereas measurable quantities such as height, weight, length, time, etc. would be continuous variables. So we want to focus on discrete random variables here. So, and we want to work out how to reframe our probability experiment so that we are able to define a numerical value to each or allocate a numerical value to each outcome rather than the outcomes being words. So when we define a discrete random variable, it's usually identified using a capital letter, and then the specific values that that random variable can take are referred to using the corresponding lowercase letter. So for example, capital X is how we define the variable, which is in this case the number shown when a fair die is rolled, is capital X, and so that means lowercase x could be any value in this particular set of values. Okay, so lowercase x represents each individual, or is a possible value of uppercase x. Okay, so uppercase x is the variable more generally, lowercase x is the specific values that it might take. So we could have a variable uppercase h, which is the number of heads observed when a coin is tossed 5 times. So that would mean lowercase h could be 0, 1, 2, 3, 4, or 5. Uppercase W, the number of wins a team has in an 8-week season. So lowercase w could be 0, 1, 2, 3, 4, 5, 6, 7, or 8. They could win anywhere from 0 times to 8 times in the 8-week season. And uppercase D is the number of days on which rain is observed in June. There are 30 days in June, so therefore there could be anywhere from 0 to 30 days on which rain is observed. So a discrete probability distribution is when we list all the possible values of the variable. So in the case of x, that would be the numbers 1 to 6. In the case of h, that would be the numbers 0 to 5, along with their corresponding probabilities. Okay. So for example, if we think about tossing a fair coin 3 times. So the sample space of this experiment we know could be head, 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 tail, head, tail, head, etc. Okay, so there's 8 outcomes. Each outcome is equally likely to occur, so each outcome has a probability of 1/8. So the probability of getting a head and then a tail is 1/8. So because we want our discrete random variable to be a number rather than something like HHH, we instead define a random variable x such that x is the number of heads observed in 3 tosses of a fair coin, and therefore it is possible for x to be either 0, 1, 2, or 3. And so this little table here is our probability distribution. So the table lists all the possible values of x, it's lowercase x, okay? They are the possible values of the variable uppercase x, which is the number of heads observed when a coin is tossed 3 times. And we list each of the possible values of lowercase x, which is 0, 1, 2, or 3, and we list the corresponding probabilities. Okay, so this notation here is obviously saying the probability that uppercase x, where uppercase x is the number of heads observed in 3 tosses of a fair coin, so the probability that the number of heads observed in 3 tosses of a fair coin is equal to lowercase x, so in this column it'll be equal to 0, in this column it'll be equal to 1, in this column equal to 2, in this column equal to 3. Okay, so what we're essentially finding here is this probability, for example, is the probability that uppercase x, the number of heads observed in 3 tosses of a fair coin, is equal to 3. Okay, this probability is the probability that uppercase x, the number of heads observed in 3 tosses of a fair coin, is equal to 2. Okay, etc. We have another alternative for this notation over here, which I'll talk about in a little bit. So that's the discrete probability distribution. List every possible outcome, every possible value of the discrete random variable, and the corresponding probabilities. So now that we have the distribution defined, we can easily calculate probabilities, such as the probability that at least one head is tossed. Okay, so the probability that x is bigger than or equal to 1 means we're going to be interested in these 3 outcomes. So we add those 3 outcomes together and we can find that the probability is 7/8. Okay. In that case, it actually would have been quicker, rather than adding 3 probabilities, to realize we're actually adding up everything except for this outcome. So the probability that x is bigger than or equal to 1 is the same as 1 minus the probability that x equals 0, and so just 1 minus 1/8 would be 1/7. So thinking about whether it's quicker to add up the outcomes that you're interested in or to subtract the outcomes you're not interested in from 1. The probability distribution can also be graphed. Okay, it is really technically just a series of four points, but we tend to sort of draw in the lines just to give, so it's clearer to see the sort of heights that you're reaching. Okay, so here we're seeing a nice symmetric distribution. We'll talk more about shape of a distribution later on. And we've got each outcome and their corresponding probabilities. You really won't be asked to draw a probability distribution yourself, and you won't see them that frequently, but it is technically still part of the course. The other thing to note here is that alternative notation. So instead of writing the probability that uppercase x is equal to a specific value, we can write that as p of x is another alternative way of saying the probability of, in this case, you know, this would be p of 0, this would be p of 3, p of 1, my apologies, p of 2, etc. Okay. I probably tend to use this notation if I'm going to write out the probability of something happening is equal to, but in this, setting up this distribution, it's often sort of quicker and easier to refer to p of x, but either way, they're interchangeable. So properties of a probability distribution. All probabilities must be between 0 and 1 inclusive, okay? So every single value here obviously has to be somewhere between 0 and 1, or else it's not a probability, and the sum of the probabilities in the distribution must add to 1. Otherwise, you've missed an outcome. There's an outcome missing if all the probabilities don't all sum to 1. Okay. All right, so those are the 2 key criteria. So let's have a quick look at an example with the probability distribution. The probability distribution of a discrete random variable y is shown below. So y can clearly take 6 different values, 0, 1, 2, 3, 4, or 5. And we've got the corresponding probabilities, but we are missing one probability here in the table. So part A asks you to find the value of A. So we want to use the fact that we know that the sum of all the probabilities must add to 1, and so therefore we know that A is going to have to be 1 minus each of the probabilities we've been given. So 0.02, 0.13, 0.38, 0.17, and 0.25. Okay, so I'll just quickly do that here. So we have 1 minus 0.02, minus 0.13, minus 0.38, minus 0.17, and minus 0.25. Okay, so A must be 0.05. Alright, then we want to find the probability that y is less than or equal to 3. So that means y could be 0, 1, 2, or 3. So we're adding up these 4 probabilities. Okay. So it would be probability of x equals 0 plus probability of x equals 1 plus probability of x equals 2 plus probability of x equals 3. Or you might instead decide to do 1 minus these two probabilities instead, which is the same as 1 minus the probability that x equals 4 minus the probability that x equals 5. And so in this case, that's 1 minus a, which is 0.05, and minus 0.25, so it leaves us with 0.7. Okay, probability that y is bigger than 1 and less than or equal to 4. So bigger than 1 means it's not going to actually equal 1. Less than or equal to 4 means it can equal 4. So this is the probability that y is equal to 2 or 3 or 4. Oops, sorry. Try that again. And so in this case, that's 0.38 plus 0.17 plus 0.05. 0.05 plus 0.17 is 0.22. Adding that to 0.38 is 0.6. Okay, then we want to think about some conditional probabilities. So find the probability that y is greater than or equal to 4, given that it is greater than 1. Okay, so we know that that means we need the intersection over the second thing, but also we've got the table here. We've talked quite a lot about conditional probability in the previous video. So probability that something is greater than or equal to 4, given that it's greater than 1. Okay, so given that it's greater than 1, given that we're only dealing with these probabilities, what is the probability that it's greater than or equal to 4? What is the probability it's one of those two things? Okay, so essentially what we're looking at here, we know our conditional probability means we need the intersection, so we need to think about when are we both greater than or equal to 4 and greater than 1 over probability y greater than 1. And in this case, the intersection of being both bigger than or equal to 4 and bigger than 1 is just the probability that y is bigger than or equal to 4. Okay, be careful about jumping straight to here, from here to here a bit carelessly. It's not always this divided by this. It just happens here that in this particular instance, the intersection of those two things is equal to the probability that y is bigger than or equal to 4, sorry. So bigger than or equal to 4 is going to be a, which is 0.05 plus 0.25, over probability bigger than y is going to be 0.38 plus 0.17 plus a, which is 0.05 plus 0.25. Okay, I might just work that out here. So 0.05 plus 0.25 should be 0.3 on the numerator, 0.38 plus 0.17 plus 0.05 plus 0.25. And sorry, the question should specify here, let's say find, let's say, everything's going on there, correct to 4 decimal places, let's say. Okay. 4 is quite a common probability level of accuracy in methods. It will often ask you for 4 decimal places. If it's different to that, it will usually be because something's going on with the numbers, or the rounding to 4 is a bit strange, or the potential for you to have compounded a rounding error means it's easier to ask you to round to 3 or 2, but often you'll be asked to round to 4 decimal places. So to 4 decimal places, that's that. The other thing, well actually, it probably didn't need to specify that. So if alright, let's say it is approximately that, but let's have a think about this. Sorry, I jumped the gun there. This is 0.3, and then we've already added up those 3 in the previous one. That was 0.6 plus another 0.25, so that's going to be 0.85. So it's 30 on 85. 5's a common factor there. That's 6 on, how many 5's in 85? There's 50 and 35, 17. 6 on 17. Okay. So yeah, sorry, it didn't specify an accuracy, so we won't round if it didn't tell us to, because we can still work it out exactly. Okay, and then the second question, find the probability that y is less than or equal to 4 given that y is bigger than 1. Okay, so still the same condition, y is bigger than 1. So we're still out of the 2, 3, or 4 or 5, sorry. This time we want the probability that y is less than or equal to 4. And so that should be less than or equal to 4 will be those 4 things there. Those 3 things there. So it is probability that y is less than or equal to 4 and y is bigger than 1 over probability that y is bigger than 1. So the intersection of being less than or equal to 4 and bigger than 1 is y being between 1 and 4, not including 1 but including 4, and we've actually already found that answer in part C. So you'll often find in these questions you'll have some of the answers that you need already. Okay, so we know that the answer to part C between 1 and 4, not including 1 but including 4, was 0.6. We've already worked out our denominator up above there, that was 0.85, and so this is 60 on 85, which is, we're dividing by 5, so it was 12, it'll be 12 on 17. Okay, so example 2, a spinner is divided into 5 equal sectors numbered 1 to 5. The pointer is spun twice and the sum of the two numbers is recorded. Set up a probability distribution for x, where x is the sum of the two numbers spun on the spinner. Okay, so we answered questions like this in the previous couple of videos, but this time we want to take it that step further once we've organised our information to then translate that into a probability distribution. So let's first organise our information. So discrete random variables and probability distributions don't remove the need for you to still be able to work with tree diagrams, Venn diagrams, probability tables in order to organise your information. Okay, so the spinner has 5 equal sectors numbered 1 to 5. 1, 2, 3, 4, 5. And it's spun twice, so we'll have our first spin and our second spin. 1, 2, 3, 4, 5. The pointer is spun twice and the sum of the two numbers is recorded. Okay, so we're going to add all these up. So we get 2, 3, 4, 5, 6, 3, 4, 5, 6, 7, 4, 5, 6, 7, 8, 5, 6, 7, 8, 9, 6, 7, 8, 9, and 10. Okay, so once we've got our information sort of organised, we know the spinner was equally divided, so each of the 25 outcomes we've got here are all equally likely to happen. But we now want to set up a probability distribution for x. Okay, x is the sum of the two numbers on the spinner. So if we think about the possible values that x can take, the smallest value we can see there is 2, and then it can take every other value, so 2, 3, 4, etc., up to 10. So that means in setting up our probability distribution, I'm going to need quite a long table because it's going to have, 9 different outcomes. Okay, so hopefully I've got enough. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So 2, 3, 4, 5, 6, 7, 8, 9, 10 are my possible outcomes. Probability of each of those outcomes. So the probability of getting a 2, there's only 1 out of the 25 cells that is a 2. Probability of getting a 3 is 2 out of 25. 4 is clearly 3 out of 25. 5 is clearly 4 out of 25. 6 is 5 out of 25, which is 1/5. Okay, but sometimes it's helpful to have them all over the same denominator. It makes it easier when you're trying to add them up. But equally, I would always give the simplified value as well. And then we're going to have, we've clearly got some symmetry here. So we've got 4 out of 25, 3 out of 25, 2 out of 25, and just 1 out of 25 ways to get a sum of 10 by rolling 2 5s, or spinning 2 5s, sorry. Okay, so once we've got our probability distribution, we want the probability that x is bigger than 4. So bigger than 4 is all of these values here. It's probably going to be easier to do that as 1 minus the probability that x equals 2, or x equals 3, or x equals 4. So that's going to be 1 minus 1 on 25 minus 2 on 25 minus 3 on 25. So it's 1 minus 6 on 25. 1 is 25 on 25, so that's going to be 19 on 25. Okay, so then the probability that x is bigger than 4, given that x is less than or equal to 6. Okay, so we want the intersection of those two things. X has to be bigger than 4 and less than or equal to 6, over the second thing, x being less than or equal to 6. Okay, so the intersection between those two things is going to be that x has to be bigger than 4 and less than or equal to 6. Bigger than 4 and less than or equal to 6, over the probability that x is less than or equal to 6. Okay, so bigger than 4 and less than or equal to 6 is just these two outcomes, okay, 5 and 6. So we're just going to have 4 on 25 plus 5 on 25, so we can simplify that to 1/5, but it's easier to add it together with the 4 on 25. And then x less than or equal to 6, we can either add up 2, 3, 4, 5, and 6, or take away 7, 8, 9, and 10 from 1. It's pretty much of a muchness in that case, so I might just add them up. 1 on 25 plus 2 on 25 plus 3 on 25 plus 4 on 25 less than or equal to 6, so it has to include 6, so plus 5 on 25. Okay, so the numerator is 9 on 25. In fact, I might write it out separately. 9 on 25, and we are dividing by, what have we got there? 1, 3, 6, 10, 15 on 25. And so if that's going to be 9 on 25 times 25 on 15. 25's cancel out. 9 on 15, common factor of 3, 3/5. Okay. All right. Then we want to talk about the idea of a measure of centre, and we also want to talk about measure of spread, and these are going to be important when we come to talk about the specific probability distributions which do remain in the course. So let's consider the following frequency table that shows the number of children in each household in a particular street. So what the table is telling us is that there are 4 households in this street where there are no children, there are 4 households where there's 1 child, 8 households where there's 2 children, etc. Okay. So I want you to think about, and perhaps pause the video here and have a think about these 2 questions here and here. How would you calculate the mean number of children per household from this frequency table, and how would you calculate the median number of children per household? So in terms of thinking about the mean, it helps you to think about what this data would have looked like as a raw list of data. So as I said, the frequency table tells us that there are 4 households where we've got 0 children. So if we were just knocking on doors, first 4 households have 0 children. They wouldn't have been the first 4 necessarily, but it doesn't matter. The next 4 would have had 1 child. The next 8 would have 2 children. 2, 2, 2. What am I up to? 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then we would have had 6 3s. Okay. Okay. So I just want you to sort of imagine that. You don't need to write it out. And we know that if we want to find the mean of a list of numbers, we add them all up and we divide by the total number of numbers. Okay. So we can work out how many numbers are in the list just by adding up the frequencies. Okay, so there's 4, 8, 16, 22, 24. So there's 25 households that have been surveyed here. So we would add all the numbers up and divide by 25. Now, we actually don't need to write out the list to add all the numbers up, because the fact that there's 4 zeros means that's 4 lots of 0. There's 4 times 1, and there's, 8 times 2, and there is 6 times 3, etc. And that's what we're going to need to add up. So to add up the total list of numbers, what we actually need to do is simply do 0 times 4, which is 0, 1 times 4, which is 4, 2 times 8, which is 16, 3 times 6, which is 18, and 4 times 2, which is 8, and 5 times 1, which is 5. That's going to give us the total number of children. Okay, so we add that up, we get 20, 38, 46, 51, I think. Let me just check that. 46, 51, yes. And have I done my multiplications right? 0, 4, 16, 18, 8, and 5. Yep, okay. And so therefore the mean number, so what we've essentially done is 0 times 4 plus 1 times 4 plus 2 times 8 plus 3 times 6 plus 4 times 2 plus 5 times 1, and we're going to divide that by 4 plus 4 plus 8 plus 6 plus 2 plus 1. Okay, so that turns out to be 51 on 25. If we get a decimal for that, it should be 2.04. Okay, so the mean number of children per household is 2.04 children, so just over 2. We don't ever round the mean, or we don't round any measure, mean, median, range, etc., and we talk about that later, because we're not suggesting any one household has a mean of 2.04 children. I know it's impossible to have 2.04 children in a house, but the mean is still giving us a sense that on average it's a little bit more than 2 per household. The average is okay. It's okay for the average doesn't have to be rounded to the nearest whole number just because you can't have a fractional child. Okay, so it's really important that you don't round the that down to 2. Unless this question specifies that you wants the mean value correct to the nearest whole number. Find the median number of children per household. Okay, so the median is the middle value. So again, if we were kind of think about our list of numbers, we've got our, 4 zeros, 4 ones, 8 twos, 6 threes, 2 4s and a 5. Okay, so that's our list of numbers. We know there's 25 numbers, which means we're looking for the middle point. Okay, so 25 numbers, the middle is going to be the 13th number. To find the middle number, you add 1 and you divide by 2. Okay, so there will be 13 numbers. If you had 24 numbers, add 1 and divide by 2 would give us 12.5, and that tells us that the median is actually between the 12th and the 13th number. So when you have an even number of pieces of data, there isn't going to be a middle piece of data. It'll be halfway between two. But here we have an odd number of pieces. The 13th one is the middle. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That will be the middle. Now, again, we don't want to write out the list to work out where the median is. So we do need to add up the list and know that there's 25 bits of data, and we do need to know that the median will be the 13th. Okay? So we then need to work out where is the 13th piece of data. And so we simply add up the frequencies until we get equal to 13 or past 13. So there's clearly, if we look at the cumulative frequency, there's 4 bits of data that are zeros. Now there's 8 bits of data that are zeros or ones. So the median is not in there. The median's still further on than that. And then we add on another 8 bits of data, and we've now up to 16. So it means that the median is going to be somewhere between here and here, which means it has to be one of these 8s, okay? Because again, you've got 1, 2, 3, 4 zeros there, 1, 2, 3, 4 ones there, it's not any of those. And then you're listing out 8 8s, one of those 8 twos, one of those 2s somewhere in that list will be the median. So the median value is going to be 2. So you add up your frequencies until you get equal to the median or past the median, and then that value, not the frequency, will be your median value. Okay, so the median is 2. Okay, so now let's think about if I gave you this exact same information as a probability distribution rather than as a frequency table. So instead of the number of households, you now get the proportion of households listed in the table. So if 4 out of 25 households have 0 children, well, 4 out of 25 is 0.16, okay? So that is simply, 4 out of 25 children means that 0.16 of all the children, of all the households, 0 children households. And so we can work out the proportions of each category, which is the same as the probability that a randomly selected house will have that number of children. So we essentially have a probability distribution here. The probabilities should all add up to 1. You can check that if you need to. And so if we want to find the expected value of n, now expected value is the phrase we use for probability distributions when we want to find the mean. So it's the same thing. It's the expected number of children we would get in a household, the mean number of children. So if we want to calculate the mean, let's think about how we did it up here. We multiplied each of the data values by the frequency, added them all up, and then divided by 25. Now this time, we're going to multiply each of the data values by the probability. Okay, so we're going to multiply, 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 multiply. We're going to add them all up. And then here we also had to divide by 25, which was the total of the frequency column. But here, if we added up the equivalent total, it would be 1, because that's how we've said the probability distribution, all the probabilities add up to 1. So we don't actually need to divide by anything. We just do probability times the data value, each probability multiplied by its data value, and add them all up. Okay, and it's exactly the same process-wise as what we were doing in the frequency table up here. Okay, so expected value of n, we write that as capital E of n, okay, and that's going to be 0 times 0.16 plus 1 times 0.16 plus 2 times 0.32 plus 3 times 0.24 plus 4 times 0.08 plus 5 times 0.04, and it should still give us 2.04 because we haven't changed anything. It's the same data, we haven't changed that. So let's just check that. I won't bother typing in 0 times 0.16. Let's do 1 times 0.16 is 0.16, plus 2 times 0.32 is 0.64, plus, sorry, it left the decimal point off that first one, 0.16 plus 0.64, 3 lots of 0.24 is going to be 0.72, but you know, you can always type in 3 times 0.24, plus, again, that would be 0.32, 4 lots of 0.08, and 5 lots of 0.04 is 0.2. And indeed, we have 2.04. If we wanted to find the median value, okay, so now we're not, if we're thinking about where is the middle, there's not 20, this doesn't add up to 25, okay, this adds up to 1. So the middle is where do we get 0.5, where do the probabilities reach 0.5? So we cumulatively add up the probabilities, 0.16, this is 0.32, so we're still not at 0.5, this is now 0.64, which means that, so by this point, so we're sort of adding up the probabilities they correspond with kind of there. So 0.5 has to happen somewhere in this category, and so the median of n is going to be 2. Okay, so adding up your probabilities until you get to 0.5. Okay, so let's have a look at an example. A spinner is divided into 4 sections labelled 1 to 4. The spinner is spun, and that and the number where, sorry, that should say, and the number where the pointer lands is recorded. If x represents this number, the following table gives the probability distribution for x. Okay, so it's a weighted spinner or a biased spinner. It's not equally likely that each of the things will occur. We want to know what's the expected thing that we would get. So the expected value for the spinner. So expected value of x, we know we take each data value, multiply it by its probability, and add all of those up. Okay, so we're going to have 1 times 0.25, plus 2 times 0.2, plus 3 times 0.3, plus 4 times 0.25. Okay, so that's 0.25 plus 0.4 plus 0.9 plus 1. Okay, 0.4 plus 0.9 is 1.3, plus 0.25 is 1.55, and plus 1 is 2.55. So we would expect to get, and it doesn't mean we can get a score of 2.55, but it means on average, if we were to do this thousands and thousands of times and work out our average score each spin, it would be about 0.255. Okay, so in the long run, that's the score that we would expect to get. Okay, again, you don't round that value just because it's not possible to actually get 2.55. It's an average. Okay, and knowing that it's somewhere between 2 and 3 tells us something as well. This is a roughly symmetric distribution. It's just slightly different here. It's just slightly heavier on this side. So it makes sense that the mean is in the middle, but it's just slightly more towards the 3 than it is towards the 2. Okay, makes complete sense given the numbers. So again, that sense of does my answer make sense when you finish calculating something is really important. Find the median for the spinner. Okay, so we add up the probabilities. So at this point, so far we've got 0.25. And then adding on 0.2, this is now 0.45, so we're not quite at 0.5. This will be 0.75, so the median has to sit somewhere in this category. So the median will be 3. Okay, so expected value of a probability distribution, it's written as expected value of x. We can also use the Greek letter mu for the mean. We tend to use mu when we're dealing with continuous distributions and e of x when we're dealing with discrete distributions, but both technically are interchangeable. It's found by summing, so we take the sum, we've met this notation before now, of all of the x values times their probabilities. Okay. And as I said here, the expected value for a discrete distribution does not need to be an integer, so you don't round it unless you're explicitly instructed to round. The median of a probability distribution is found by adding the probabilities from the smallest value of x upwards until the total exceeds 0.5, in which case the value of x that has been reached is the median. The total is exactly 0.5, in which case the median is the mean of the x values that's been reached. So let me just have a look at the previous example to see what would have happened. So let's say that this probability was actually 0.25, okay, instead. So obviously something, let's make that 0.20 to make it the same. So this time, when you add up the probabilities, you would have found they added to exactly 0.5 here, which means the median is exactly halfway between this category and this category. So then what we do is we average those two values, and we find that the median in that case would be exactly 2.5. Okay, so that's what that little table is referring to there. Okay, let's have a look at one more example, and then we'll talk about spread. A marble is randomly selected from a bag that contains 6 red marbles, 3 blue marbles, and 1 yellow marble. The game costs $3 to play. If a yellow marble is selected, you receive $8. If a blue marble is selected, you get your money back, and if a red marble is selected, you receive nothing, so you lose the $3 that you paid to play. Is this a good game to play? So we essentially want to work out what is the expected win. In the long run, what would be the expected win? And if on average it would be expected loss, it's not a good game to play. If it would be an expected gain on average, it is a good game to play. If you break even, doesn't really matter, so the expected value is 0. So we essentially want to work out the expected value. So let G be the amount of money you gain in a game. What are the possible values of G? So G is not just what you sort of get paid, it's your overall gain. So it costs $3 to play. If a yellow marble is selected, you receive $8. So that's a gain of $5. Okay. If a blue marble is selected, you get your money back. So that would be a gain of $0. And if a red marble is selected, you receive nothing. So you lose your $3 that you paid. So those are the possible values of, lowercase g, to represent the specific values of uppercase G. So the values are 5, 0, and -3. So we want to then set up a probability distribution for G. Okay, so probability that, uppercase G is equal to lowercase g. We'll list out possible values of lowercase g. I'll list them in numeric order, so I'll put the -3 first, 0, 5. And then we want to work out the probabilities of those things happening. So this is where we then need to organise the probabilities. Oh, in this case, I was thinking it was a tree diagram, but it's not, because we're not making more than one selection. So the bag has 6 red marbles, 3 blue marbles, and 1 yellow marble. So we lose $3 if it's a red marble, and we gain nothing. We get our money back if it's a blue marble, and therefore we win if it's a yellow marble. Okay. So each of these probabilities is going to correspond to the probability of selecting a red or blue or yellow. So probability of selecting a red, we've got 10 marbles there, and 6 out of the 10 are red, so that's going to be 0.6. You can write it as 3/5 if you want, not as 6/10 though. Probability of choosing a blue marble is 3 out of 10, so that's 0.3, and therefore the probability of choosing a yellow is the remaining 0.1. So there's our probability distribution for G. In the long run, how much would you expect to win or lose per game? So we want the expected gain. Okay, and the expected gain is going to be -3 times 0.6 plus 0 times 0.3 plus 5 times 0.1. So it's going to be -1.8 plus 0 plus 0.5, and so -1.3. Right, so therefore, in the long run, you would be expected to lose $1.30 per game. So this is not a good game to play. It doesn't mean that you won't win occasionally in any way. It just means on average you should be expected to lose $1.30 per game, and so therefore over the long run you would be losing. So therefore not a good game to play. You want something where maybe the expected value would be closer to breaking even or even positive. Although, realistically someone setting up such a game is not going to set it up in a way that the expected value would give them a loss. Okay, the final thing we want to talk about is these ideas of variability, these concepts of variance and standard deviation. And once again, this is important background to understand what these concepts are when we talk about the specific binomial and normal distributions, which do remain in the course. Okay, so the first thing we want to talk about is variance. Variance is denoted var x, variance of x, or we can also use sigma squared. And once again, we tend to use sigma squared more for continuous variables and var x for discrete, but they are both technically interchangeable. Okay, so we want to work through the process of, there's a computational formula that allows us to work out variance, and we essentially want to kind of establish that. So technically, variance is the average of the squared distances from the mean. So that is that the variance of x is equal to the expected value, so the average of the square of x minus the mean. Okay, so if you take x minus the mean, you're subtracting the mean from each of your x values, you're calculating how far each x value is away from the mean. Then you square that okay, and then you take the average. So you're getting the average of the squared distances from the mean. So it's giving a sense of how far away is the data from the mean. A bigger variance will mean it's more spread out, a smaller variance will mean it's less spread out. Okay, so let's have a think about the process of averaging the squared distances from the mean. So let's look at two very simple data sets, each containing just 6 numbers and both with a mean of 5. Okay, so the first thing we do is that we subtract the mean from each piece of data. Okay, so I've calculated the mean of 5, you can check that. You subtract the mean from each piece of data, so -5, -5, -5, -5, -5, and -5, and you get these numbers here. Okay, so essentially what this is telling us, this -4 tells us that this piece of data is 4 below the mean. This +3 tells us that this piece of data is 3 above the mean. So it tells us how far away we are from the mean. So it would be helpful, it would be a measure of spread to just look at how averaging the distances from the mean. But in terms of calculating that, that's more complicated because when we subtract the mean, we get positives and negatives. And if I were to just average these, it wouldn't actually give me an average distance because the negatives are interfering. So in order to get rid of the negative problem, we're going to square all the numbers. So -4 squared, -2 squared, etc. So we square all the numbers, so now we have positive numbers. And we've done exactly the same process here. Subtracted the mean, subtracting 5, and then squaring each of the values. Okay? And squaring has now eliminated the negative problem. So now these are squared distances from the mean. This 16 is indicating that this number 1 is essentially the square root of 16 away from the mean. Okay, this number 8 is the square root of 9 away from the mean, but we've lost the positive or negative, which now it doesn't tell us whether it's bigger than or less than the mean. It's just telling us how far away it is from the mean, the square of that. And then we can average these numbers. So we average these numbers. In this case, we get a variance of 7 2/3. In this case, we get a variance of 33 2/3. So much larger variance here, indicating that the data is more spread out. And if we go back to the original data, it is more spread out. The mean is 5, that's sort of somewhere here, and the data ranges from being 4 below that to 9 above that. Here the mean is 5, and the data only ranges from being 4 below that to 4 above that. Okay, so it's a lot less spread out. So therefore we get a smaller variance. Now the value of the variance in itself doesn't really tell us anything. 33 2/3 doesn't really correspond to anything in particular to do with the data set. Well, it is the average of the squared distances. So the square root of that would be the average distance from the mean, and that's a more useful spread, and we call that standard deviation. We'll talk about that in a minute. Okay, so let's have a look at this process again in the context of a probability distribution. So I've done all the maths here just to talk through, just to make a point. So a game is played in which it's possible to win $0, $5, or $10. If X is the amount won, the probability distribution is this. And so we can work out the expected value of X just as we looked at before, and it is 1.25. So in order to calculate the variance, we would be subtracting the mean from each of the data values, so subtracting 1.25, which is what's happened from that first row to the second row. Then we square those values, that's what's happening from the second row to the third row. Okay, and now we've got a distribution that is, if we just look at this bit here, it is the squared distance from the mean corresponding with the probabilities. And then we want the expected value of that, and so we do the value times the probability plus the value times the probability plus the value times the probability. Okay, so that's what's happening here in this row, and we find that we get a variance of 7.1875. Now, we actually don't tend to use this formula for finding variance, though having an understanding that that's what you're finding when you're finding variance is important. We can actually use something called the computational formula, and that's sort of derived here. If you think about the fact that the variance of X is the expected value of X minus the mean squared, if we expand out that perfect square, X squared minus 2 times the mean times X plus the mean squared, and then if we're calculating the expected value of these three things added and subtracted together, we can just do the expected value of each. So expected value of X squared minus expected value of 2 mu X plus expected value of mu squared. Okay, this is a number, we'll talk a bit more about this later, but that can come out of here, so that's just 2 mu times the expected value of X, and the expected value of the mean squared, that's just a number, so that is just the mean squared. Okay, and so essentially what we have here is this is the mean, this is the mean, this is the mean, this is, so you've got expected value of x squared 2 times the mean squared, okay, plus the mean squared, and then we can collect together these like terms here and we get this formula here. So again, don't worry too much about following the derivation of the formula. The point is that this is actually the formula we use to calculate variance. It's more practical. So we calculate the expected value of x squared, and then we subtract the expected value of x all squared. Okay, so expected value of x squared, we do that simply by squaring each of the x values and then multiplying by the probability. Okay, so instead of just doing the x value times the probability, we do the x value squared and then times it by the probability, and we get 8.75. And so it's 8.75 expected value of x squared minus the expected value of x, which we worked out at the top as 1.25, all squared. And we get 7.1875. So we verify that it does indeed give the same value as what our expected value of the squared distances from the mean gave. So this is the formula that we'll use in practice. Expected value of x squared minus the expected value of x all squared. Okay, and then I mentioned the idea of standard deviation. So in the process of finding variance, because we square the distances from the mean, and what we're getting then is an average of the squared distance from the mean, it's a bit meaningless in terms of what we're measuring. So for example, if x was in dollars, then the variance is being measured in square dollars, which is a completely meaningless unit. So to correct for this problem, we can then take the square root of the variance once we've calculated it. And that is another somewhat more useful measure of spread, which we call the standard deviation. And the standard deviation is in the same units as the random variable, and it is giving you the average distance of each piece of data from the mean. Okay, so it's a more direct measure of spread that you can sort of get some context around what it actually means and what it's actually telling you. The last thing I just want to run through is the expected value and variance of a function of x, and usually I go through sort of a whole lot of examples that we work through together, but I'm really just going to give you these formulas here because they're not really going to come up so much this year, I wouldn't expect. Generally, if we wish to calculate the expected value, variance or standard deviation of a function of x, then we must first establish a new distribution before we can calculate the expected value of x. So that's pretty much what we did when we did expected value of x squared. Okay, we had to calculate a new distribution where we worked out the x squared values, and then we just calculated the expected value of x as usual. Okay, so we have to do that process when we calculate variance of x. However, there is one exception, and that is if the function of x is a linear function. In this case, the expected value variance and standard deviation is directly related to the original expected value variance and standard deviation. So if we have the expected value of a linear function of x, so if we want to know what the expected value of 2x is, it is just going to be 2 times the expected value of x. If we want to know what the expected value of 5x minus 3 is, it is just going to be 5 times the expected value of x minus 3. Okay? Only when it's linear can we essentially kind of expand it out like that. The variance is going to be, and usually I would deal with sort of why this happens a bit, but I don't think these are going to come up, so I'm not going to worry about it this year. So the variance of a linear expression is simply a squared times the variance of the original variable. So variance of 2x, variance of 2x would simply be 2 squared times the variance of x, so 4 times the variance of x. The squaring is happening because of the squaring process in the variance calculation. Similarly though, it's interesting to note that the variance of 2x plus 3 is just going to be still going to be equal to just 2 squared times the variance of x. And that's because if you think about, if all you're doing is adding 3 onto all of your x values, you're not changing how spread out they are, so you're not changing the variance in any way. Whereas if you're doubling all your x values, they're becoming more spread out. So the variance is being changed, it's actually being changed by a factor of 4. But if you are only adding or subtracting onto each of your x values, you're not actually changing the spread, and so that's why the b value doesn't affect the variance at all. Standard deviation of a linear function. So we know that standard deviation is the square root of the variance, okay? And so that means the standard deviation of ax plus b is the square root of the variance of ax plus b, and we know that the variance of ax plus b is a squared times the variance of x, and so then we've got the square root of a squared times the standard deviation. Now it's worth noting that there's a slight problem here. It's not just as simple as being a times the standard deviation of x, because if the a value is negative, by the time you've squared it and square rooted it again, it won't be negative anymore. So it's just the magnitude of a, so ignoring any negative signs. So for example, if you were calculating variance of 3 minus 2x, so a is negative 2, the variance of that would be negative 2 squared times the variance of x. But the standard, if you wanted the standard deviation of 3 minus 2x, it's not going to be negative 2 times the standard deviation, it's just going to be 2 times the standard deviation. You can't have negative standard deviation, okay, nor negative variance. It's a measure of spread. How far away from the mean are you? It's not got any direction. Okay, I think this is probably the last example. Yep, one more example here. So for the random variable y, defined as follows, let's sort of put everything together. Let's find the expected value of y, so that is going to be 0 times 0.06, plus 1 times 0.28, plus 2 times 0.43, plus 3 times 0.23, okay? And so that is going to be 0 plus 0.28 plus, what's that, 0.86 plus 0.69. Let's just add them up here just to be careful. 0.28 plus 0.86 plus 0.69. So expected value of y is 1.83. Expected value of y squared would be 0 squared times 0.06 plus 1 squared times 0.28 plus 2 squared times 0.43 plus 3 squared times 0.23. Oops, 23. Okay, so that's still 0, that is still 0.28. Then we've got 4 lots of 0.43, which is 1.72, and then we've got 9 lots of 0.23, which is 2.07. Alright, so we add up 0.28 plus 1.72 plus 2.07, and we get 4.07. Okay, this in itself is a bit meaningless, but it's part of the process that we need to calculate variance. We know the variance of y is the expected value of y squared minus the expected value of y all squared. So in this case, that is 4.07, our answer from part B, minus 1.83, our answer from part A, all squared. So 4.07 minus 1.83 squared is 0.7211. And then we want the standard deviation of y, which is, and we probably need accuracy here, let's say 2 decimal places. Standard deviation of y is the square root of 0.7211. So I haven't rounded anything up to this point, but this one's going to need rounding because it's a irrational number. So let's go with 0.85. Okay, it's the standard deviation of y. So on average, each data value is 0.85 away from the mean. Okay. Our mean is 1.83, somewhere here. On average, each data value, if we were to average the distances away from the mean, you should find that it's 0.85. Okay, then we want the expected value of 3y plus 1. Now, because this is a linear function, we can essentially just expand this out. So this is 3 times the expected value of y plus 1. So that is 3 times 1.83, which we found in part A, plus 1. And so that is 6.49. The variance of 3 times y plus 1, so that is going to be 3 squared times the variance of y, which is 9 times, and the variance is 0.7211. 9 times 0.7211, which is 6. I think that's exact, yep, 6.4899. And then expected value of 5 minus y, so again, this is a linear function, negative 1 times y plus 5. So this is just going to be 5 minus the expected value of y. So that is 5 minus expected value of y was 1.83. Oops, 1.83. 3.17. And then the standard deviation of 5 minus y. Okay, so remember it's the absolute value of negative 1 times the standard deviation of y. Have I worked out? Yeah, I've got the standard deviation of y. So actually it's just going to be positive. It's just going to be equal to the standard deviation of y, which was 0.85. So let's just go with that same 2 decimal places here. Okay, so that's a bit of a discrete random variables in a nutshell. So that idea of what is a discrete random variable, what is a probability distribution, how do we set it up, how do we use it to calculate probabilities, how do we calculate the centre, and the centre of a distribution can be measured by mean or median in maths methods, and how do we calculate the spread, which can be measured by variance or standard deviation. Okay. Over the course of the next few lessons, we'll now start to talk about the binomial distribution, which is a specific example of a discrete probability distribution, and we will also talk about mean, median, maybe not median, variance, standard deviation, etc. in the context of the binomial distribution. If you want to have a bit of a go at this work, these are the questions I would usually set from 13C and 13D. By all means, you can have a little dabble around in there and have a play if you need, but I'm not going to insist that that work be completed. We'll move straight on to the binomial distribution in our next video.